Hello everyone, my name is Ashley Goodnight and this is my Reading Week 11 video. This week we covered modeling friction. We looked at the example of pulling a box across a surface. In terms of thermal energy, we know that if there's friction, the box should become a bit hotter since friction is a dissipative force. We attempt to prove this mathematically through the energy principle. We first drew a free body diagram of the situation. Since we're looking only at the x direction, we can ignore the normal and gravitational forces in the y direction. Next, we can write out the energy principle. If we know the box is moving at a constant speed, according to Newton's second law, the F applied and the force of friction are equal and opposite. But this doesn't make sense in the energy principle. It would mean that there is no change in thermal energy. Well, we need to think a bit more on the friction force. If we take a closer look, a microscopic look, at the object's contact with the surface, we can see that the rough surface has pockets of air. This means that the overall displacement of the friction force is less than the displacement of the center of mass. Going back to the energy principle, this means that there will be an overall gain of thermal energy, which logically makes sense. This week, we covered collisions in one dimension. I have some prior experience with this concept from my high school physics class. I know that all collisions retain conservation of momentum, but not all collisions have conservation of energy. During what's called inelastic collisions, there is a loss of energy in the system due to thermal, rotational, or vibrational energy. Building off of last week, we returned to multi-particle systems with the concept of conservation of momentum. I've never used it in terms of a multi-particle system. For a multi-particle system, we've already explored finding the center of mass of the system. Well, we can also find the momentum of the system using Newton's second law. Momentum of the system equals the sum of the individual momenta. If we take the derivative of this form, we end up with dp dt, which we know equals net force. Analyzing this equation, we see that the internal interactions cancel one another. As a final note, we also have the ability to choose our own system, which allows us to use conservation of momentum in multiple situations. For me, the most mathematically difficult aspect was the lecture on glancing collisions. I did a bit of searching and found an article on lumenlearning.com under their linear momentum and collision section. It walked through the different concepts for glancing collisions. It highlighted learning objectives, key takeaways, helpful diagrams, and worked through the math. If you ever struggle with collisions, this is definitely worth your time to look through. This week's lessons apply to my major of electrical engineering. Georgia Tech offers ECE majors the opportunity to focus their studies around sensing and exploration. This field is dedicated to sensing our surroundings and communicating via those senses. This week's lectures reinforced our ability to predict future motion with main physics concepts like the momentum principle and collisions. Part of sensing our surroundings is predicting what our surroundings are doing and going to do in order to better react. With that, I am concluding my presentation. Thank you everyone for listening. See you all next week.